The design of a slit lamp provides such a tool. The slit lamp has a moving observation system, the microscope, and a moving illumination system, the slit beam. The actions which are used for generating the optical phenomena can be described by two angles, the illumination angle and the observation angle. Let us describe first the illumination angle. The illumination angle is the angle between the light beam and the observer, that is, the microscope. Please note these pictograms which will be used throughout the following sequences. Basically, there are three main directions of an incident light beam. Light from the direction of the observer, that is, from the front, then the angle between observer and the light beam is about 0 degrees. Light from the sides, the illumination angle is about 90 degrees. And light from the back. The illumination angle is about 180 degrees. Every illumination angle provides different information about an object. An optimal examination strategy means do not just look at what you see. Skilled examiners look for what they want to see. For example, for the detection of minimal turbidity, that is, a minimal imperfection of transparency. Light scattering is generated. This is demonstrated here in a cube filled with smoke, which is invisible unless a bright light beam renders its even minimal turbidity visible through the so-called Tyndall phenomenon. For the evaluation of a surface, reflexes are generated. This is demonstrated here by the cube on which reflexes make the surface visible as well as some scratches now seen on this surface. For detecting transparent objects with a different index of refraction, the deviation of light coming from the back is examined. This is demonstrated here by glass balls in the transparent cube, which have black margins because light coming from the bright background has been refracted away. And for the evaluation of the degree of a localized intransparency, the absorption of light coming from the back is examined. This is shown here by black balls in the cube which prevent the light from the background from reaching our eyes. So 4 optical phenomena can be used for the examination of transparent media: light scattering, reflection, refraction, and absorption. What illumination angle should be chosen for slit lamp microscopy? The choice of the angle in a given situation depends on the goal of light application. These angles shall be explained by a case of chronic anterior segment inflammation. If the goal is the generation of light scattering, the illumination angle should be as close to 90 degrees as conditions permit. This is shown by the cross-section through a lens, which, although transparent, becomes distinctly visible. Here it is in sharp focus at the anterior cortex. Here at the center at the lens nucleus, and here at the posterior cortex where a subcapsular cataract exists. If the goal is the generation of reflexes, the angle should be variable, as shown by reflexes here at the anterior lens surface and here at the posterior surface. If the goal is the evaluation of the effects of absorption and refraction, the angle should be 180 degrees. This is shown in this posterior subcapsular cataract where the phenomena of absorption and refraction are seen in backlight with fine details shown at high magnification. Not all angles can be obtained by direct illumination due to anatomical constraints. If direct access of the light to the target is impossible, one has to use indirect light produced within the eye. This is achieved by projecting light against a non-transparent tissue such as the red fundus, which then acts as a reflecting screen. Other sources of indirect light are the iris and, in some conditions, the lens. Thus, the eye interior can be transformed into reflectors for generating indirect light. For observing an object in indirect light from the fundus, the light beam is directed away from this object towards the background. There, the rays are reflected. They will provide backlight, also called retroillumination, for a target which is far away from the fundus. A target which is very close to the fundus may also be illuminated from the side, and this is called lateral indirect illumination. Similarly, the indirect light from the iris can be obtained by directing the beam away from the target towards the iris, and from there, backlight and lateral indirect light are produced. In addition, even a transparent medium such as the lens can be made to be an indirect light source by reflexes at its anterior or posterior surface, or scattered light produced within the lens. With this in mind, we will now discuss the illumination techniques for the generation of optical phenomena in more detail. What is the purpose of the examination of light scattering? It allows the visualization of minimal imperfections of transparency which otherwise are invisible. In the eye, it is used for the visualization of the cornea and the lens. Here, the light scattering phenomena are quite strong. Scattered light is further used for the detection of weak pathological phenomena in the anterior chamber, which are nearly invisible here but can be made visible by using proper techniques. The best technique for generating light scattering is an illumination angle of 90 degrees, but this is only obtainable in the anterior segment. The more posteriorly the examination proceeds, the more restricted the choice of a large illumination angle becomes, and the conditions for examination with scattered light deteriorate. How can we optimize our observation of light scattering? This can be done by choosing a dark background, maximizing the sharpness of the margins of the light beam, maximizing the brightness of the light beam. An excellent dark background is, for example, the black scattering. The light beam should be made sharp and short so that both margins can be observed against the dark background. Comparing the area of scatter and the non-scatter vicinity improves the identification of very faint scatter. And finally, scattered light can be increased by maximizing the brightness of the light through hypervolting the light bulb. Hypervolting also proportionally increases the contents of short wavelength rays, which are especially effective for generating scattered light. Both the maximum of brightness and of sharpness of a given light source exist at the focus of the light beam. Therefore, the observation of scatter is optimal if the focus of the microscope is exactly at the same place. In other words, the focus of the light beam and of the microscope should precisely coincide. The coincidence of focus is an essential feature of slit lamps and will be discussed in detail later in this series.